Hi, how's it going? I'd like to basically go over the Leetcode problem called level order, where essentially what they want you to do is they want you to go through a binary tree and actually print, not really print, but you're producing a list of lists, which is made apparent by the return type here. You're producing a list of lists, and the list of lists will essentially contain sort of a representation of the tree in a level order fashion. So what I mean when I say that is, and let me go ahead and take this slightly down here. What I mean when I say that is if you have, let's say, a tree, and let's say this is A here, this is B here, this is C here, and then let's suppose this is D, E, F, and G. Now, what we mean when we say level order is that you're essentially moving through the elements in this manner. So what the list you'd produce, so you're moving level by level instead of node to node on a node to node basis. And so what your list of lists would be is it would be, okay, you'd have A as one list because that represents the first level of the tree. And then you'd have another list that contains B and C because that would essentially be the second level, or the first level if your numeration is from 0 to 1. And then the other list would be D, E, F, and G. And so here you have a list of lists in the same fashion that the problem wants you to produce it in. And so this would be a level order, it would be a level order traversal here, which is a very common template for breadth first search problems. But nonetheless, I wanted to essentially walk through this code as it's done here. So what we begin by doing is we begin by actually introducing a resultant, and the resultant will be a list of lists. So we can think of this as sort of an overarching list. And the idea now is that you're going to have lists inside here, multiple. So the idea here is that if you enter in a tree and you want to enforce the level order traversal on that tree, and the root is null, then you essentially just want to return the result, which would be an empty list. It would be an empty list of lists. And so this sort of takes that possibility into account. So our code is able to accommodate an empty input. And here you have a queue data structure underpinned by a linked list. And what we can think of a queue, infamously a queue is, it's popular that, it's common knowledge to know that a queue is a, first in, first out data structure. So first in, first out, where, you can think of people in a line here, and whichever was first in the line comes out. Whereas if we think of something like a stack, a stack is, they're one on top of another. And so, the first one in is actually, or the first one in, which would be the bottom one here, is actually the last one out, because you'd have to funnel through the rest in order to get to the bottom one. But nonetheless, you have a queue here. And what you do is you actually add the root of the tree into the queue. So this will be, this will be our result. This is our resultant. And this here is our queue. Let me go ahead and move this slightly over this way. So this is our result. And this here is our queue. And the idea is that we add the root. So the root we know is A, just going off the basis of this here. The result is A, or the root is A rather. And while the queue is not empty, so this is where we begin performing an iterative action. So while the queue is not empty, our first step is to actually save the size of the queue as it stands in its current position. And why we're doing that is because we want to actually iterate through, like we want to be able to iterate through and perform an operation for as many times as there are elements in the queue. And that, so the merit of saving the size of the queue will help us when we want to perform a certain operation for as many elements as there are in the queue times. So we save the size. So the size is equal to 1 in this case. So we've saved the size. And then we actually create another list. So this time we're creating another list. This list for this iteration will represent the current the current level. So what this is essentially going to be is it's going to be, if we're on the first level, this list will just be populated with A. If we're on the second level, this list will be populated with B, C. If we're on the third level, it will be populated with the contents here. So this is sort of preparing one of the entries into the list of lists. So this is just one entry here, right? And this entry, this current level, after we have everything on the current level, we will then take this and actually put it back into, we will append it to the resultant up here for that iteration. And then we do that iteratively. And then you'll see how that works. So, we created current level, and, so now we perform an action once because size is equal to 1. So this whole section here is what all it's doing is it's performing one action size times. And that action is nothing but taking this element, removing it from the queue and putting it here, and then adding both of its children into the queue. So both of A's children, which are B and C, into the queue. That is what it does on each iteration. It removes and adds its children, removes and adds its children. So I explained that to you in words. We'll see how that works in the code here. So it creates a new node. So all of this is just adding, removing, and then adding children. So, this whole thing is just removing and then adding its children. So what it does to remove is it creates a tree node called current, and it then, accesses the remove API on queue to actually, what remove will not only remove something from the queue in a first in, first out manner, obviously, because it's a queue, but it's also going to store, or it's going to return that value. So the queue API removes it from the queue, but it also returns that value, and that value will be what was removed. And so that is stored in current. That will be stored in current. And so then what happens is then you add what you just removed from the queue, you add that into, the current level. And once you do that, so you remove this from the queue, and then you add that into, the current level. And so you can think of this as the removing part and this as adding the children part. Okay, so this is the removing part, and this is the, all of this here is the adding the children part. So after it removes, it then asks, okay, well, let me now add its children into the queue. Now it has to do this for, when you think of A has B and C, right? As children. So it has to do something for B, but then it also has to do something for C. So for B, it's essentially going to say, okay, well, if it has children here, and another way of expressing that for the left of A is to say that if the current we're on A dot left is not null, then there is a child there. So in that case, add that value current dot left, add that that node, so to speak, into the queue. So it ends up adding B into the queue, and then of course it adds C into the queue as well. Now this works because with binary trees, the property is that you only ever have with the binary tree, you're only ever limited to 2 children. So this will work for each node. And once you've added those, once you've removed the one of them and added the children, now you come back up and suddenly the queue, it's not empty anymore. You've just added 2. It would have been empty if you hadn't added the children of A, but now there are 2 children in the queue. And so now you recalculate the size. So we will take everything we have here. We will take everything we have here, and we will basically now accommodate this for what the second iteration would look like. This is exactly what the second iteration looks like. However, what was done on the previous, and actually I think maybe I conflated this a little bit, or crammed it up a little bit, but what we've done before moving on to the second iteration is we've actually added this current level thing that we were just populating. We add this to the result. So instead what's going to happen, the second iteration, what's going to look like is the result would have stored this A here, right? You're going to, so that this, remember, this list that we have here represents what the current level looks like. And so after we have populated the current level, and of course we've done some pre-processing for the second iteration, we take current level, we add it to the list here. And that's why our second iteration looks like this. And this is actually this is overridden, sort of overridden. You actually create a new list on the second iteration. This size is overridden. Because what happens is on your second iteration, you actually say int size will equal q.size again. So your size will not be what it was before. Now you introduce, the size was now what the q.size is on this, which is 2 now, isn't it? So, so then what happens is, okay, well, so you say it's q.size. Now you then produce another current level. That's why I said this current level was overridden. So now you have another current level, and that makes sense, right? We want to clear out, we want to clear out memory for what the current level was before, because we want each list to represent the current level at a given time. And so ideally now what you do is you say, okay, well, you've removed, so now you remove. Again, this is a 2-step process here on each iteration. Now you've calculated the size, you created a new current level. Now you remove from the queue, so you'll actually end up removing B, and you're storing that in current.val is added to the current level. So you actually have B in the current level. And then you add B's children, right? That's what this whole idea does, is it adds B's children. You look at current.left. If that's not null, add it to the queue. If current.right is not null, add it to the queue. So remember what B's children were. It was D and E. So you actually end up adding D and E to the to the queue. And again, I mean, now you're no longer doing this for 1 iteration. You're actually doing this for 2 now. So because size is 2. So you actually, after you do that, you come back up again and you say, you recalculate the size. Now the size is 1. Or actually, you don't recalculate the size. You've done that for 1 iteration. You come back up to the for loop. Then you repeat the process again. You have a current value, which is, so you remove C now, and you've removed it from the queue, and you add it to the current level list, and then you're adding both of its children, right? You're adding both of its children from the queue into the current level list. So you go to, we've just removed C, so we add F and G into the queue F and G. And then again, so, you've now performed this operation twice, which is what size represented. So you only wanted to do this twice. So now that you've done this, this is now a representation of your current level, which makes sense because, for this level, we only have B and C. And then at the end, for that iteration, we add, the current level list that we had here. We add this to the result, which is on, which would be here. So we add BC as a entry, B comma C as an entry. So let's see that here. So we'll. So we know a few things that BC has been added as a result. And, we also know, let me take away this clutter here. We also know, or actually, maybe I'll keep the bars up a little bit. We also know that, when you come back in, the size will be recalculated. So this size is actually going to represent 4 now. And then we know another thing, which is that you actually override the previous current level and you actually end up creating a new one. Okay, this is now your new current level, right? And so you know that you overrid the size, you know that you create a new current level, you know that both of those things. And then this for loop now runs for 4 times because your iteration is determined by size. Size is 4. So now you end up doing something 4 times. What do you do 4 times? Current stores the value. So you end up doing D. And then you append both of its children. D does not have any children. None of these guys have any children. So you actually don't end up having any children in the current value level list. So D, what ends up happening is that you remove D, you also end up removing E, and you're not putting any of its children back in the queue because it has none. And therefore, what happens is that after you do this operation 4 times, you append this current level list. You append this current level list into the resultant. So now you end up having DEFG into this list. And then it's just a matter of adding. So we did add that, and then we return the result at the end. And this is your result, which is, again, this is exactly what we wanted before. We wanted because we had a tree, we had A at the top, right? We had B, and then we had C, and then we had A, B, C, D, E, and then F, and then G, right? So we had this, one of the lists were this, one of the lists were this, and one of the lists were this. So we have the current level here. And so, that sort of achieves the purpose in that regard.